In this tutorial, we'll talk about the analysis of prototype low-pass filter. Please understand the numericals and the basic formulas for a constant K type low-pass filter has already been discussed in another video. I'll put a link in the description for that as well. But in this video, we'll focus on the derivation part of all the formulas that we used there. We'll find out the derivation for cutoff frequency, the constant K, and the characteristic impedance in the first place. So for a low pass filter of T section, in this video we'll talk about T section first. Let us say we have a T section low pass filter or T type low pass filter. So how do we find the characteristic impedance of this low pass filter? Because in order to find the characteristic impedance, we simply need to remember one key point here, and that key point will make the things so easy for you. And that key point is that the filters are symmetric devices. And how can we make this device symmetric? If we connect a load here, let us say I've connected a load ZL here, and this Z0 is the characteristic impedance. So this device being a symmetric device, it essentially would mean that we'll need to keep this ZL to be equivalent to Z0. Only then this device will become symmetrical, because Z1 by 2 and Z1 by 2 are equal, and Z2 is the balancing arm in the shunt. So in order to make this device symmetrical in entirety, the characteristic impedance would come out to be equivalent to the load impedance. So that's the key point here. So filters are symmetric two-port networks, and therefore ZL must be equivalent to Z0, and Z0 is something that we are striving to find out. So, or in other words, you would have seen ZOT in the books, because once we get to ZOT, once we find what is the characteristic impedance of this filter, we can easily put in the values of L and C in order to find cutoff frequency and so on and so forth. But first things first, let's find out the value of ZO, or characteristic impedance, or ZOT in particular for a T section. So as you can see, this looking from this vantage point, let us say this is port 1 dash. If we look from port 1 and 1 dash, we'll see that Z1 by 2, this is in series with this arm, parallel this arm. So that is what I've written here. If you look from the port 1, you'll see that Z1 by 2 is in series with Z2 parallel this series arm, and this series arm has an impedance of Z1 by 2 plus ZL. So that's the first point of starting. So this is pretty elementary. You're simply calculating the total impedance as seen from port 1. In the next step, I've just used the formula for parallel impedances. So Z branch 1 into branch 2 upon branch 1 plus branch 2. So that's also very simple. And in the next step, what I've done is I've taken the LCM. The LCM becomes Z2 plus Z1 by 2 plus ZL, and this gets multiplied in the numerator part for this thing. And in the next step, I've cross multiplied, and the denominator goes to the left hand side. Now please understand, after this point we will take up this issue that ZL needs to be put equivalent to Z0. So we find a ZL here, we find ZL here, and we find a ZL here. So what we do is we put ZL to be equivalent to Z0 in the next step.
क्या आपके बाल सामने से झड़ चुके हैं? तो ऐसे बैठे रहने से कुछ नहीं होगा. यही सही समय है एक्शन लेने का.
To be equivalent to Z0 in the next step. So by doing so, this Z0 Z2 gets cancelled with Z0 Z2 here. Z1 Z0 by 2 gets cancelled with Z1 Z0 by 2 because we have substituted ZL as Z0. And finally what we are left with is Z0 square on this side and Z1 Z2 because there are two of them, Z1 Z2 by 2, Z1 Z2 by 2, and then Z1 square by 4. And finally you get Z0, which is the characteristic impedance, to be equivalent to Z1 Z2 plus Z1 square by 4. And you see this formula written everywhere in the books as the starting point of derivation of a prototype low pass filter. So that is how we get to this point. The only point that we need to consider was that the ZL should be equivalent to Z0, and that is how we can calculate the characteristic impedance because of the symmetry of these devices. Filters are symmetric two-port networks in the first place. So once we find the value of Z0, we can go on to design our low pass filter. Now we know the definition of a low pass filter and everything, why inductor is connected in the series arm, why capacitor is connected in the shunt arm. That has already been discussed in the previous videos. So we know that the series arm Z1 has a total impedance of j omega L because L1 by 2, L1 by 2. So this is known to us, and the shunt arm has the total impedance 1 upon j omega C. Now we can compare this with the previous standard two-port network notations, where Z1 is the sum of these two and Z2 is the shunt arm. So having said that, we know that our formula has Z1 Z2 and Z1 square upon 4. So what we do is we calculate the values of Z1 Z2 and then we'll substitute these values here. So Z1 Z2, when calculated, this gets multiplied by this, so we get L upon C, and the value of Z1 by 4, Z1 square by 4 comes out to be minus omega square L square upon 4. And when you substitute this and this into the characteristic equation, characteristic impedance of the two-port network, which is a filter in this case, you get ZOT to be equivalent to L by C minus omega square L square upon 4. And we take L by C common, so what we get, we get a 1 here and omega square LC upon 4. Now this L upon C will always be a real quantity because L is some numerical value, C is some numerical value, and we have an under root of that, so this will be some real quantity. And this thing in the under root will be real only if omega square LC upon 4 is less than 1. If this quantity is lesser than 1, then the entire thing, the under root, will be positive and it will be real. So we need to focus on condition number 1. Condition number 1 says that my ZOT, my characteristic impedance of the filter, will be real only if omega square LC upon 4 is less than 1. and it will be imaginary when omega square LC upon 4 is greater than 1. Now, offering a real impedance means that the circuit would actually oppose the signal, and offering an imaginary impedance is the opposite of that. And what will be the cutoff frequency? The cutoff frequency will be when ZOT becomes exactly equivalent to under root LC, or this entire thing vanishes, when the dependence on this term goes away, because this is the demarcation point of when the filter will give you a real impedance versus when the filter will give you an imaginary impedance. So from here, omega square LC upon 4 is equal to 1 is a condition of the cutoff frequency. So what you can do is you can simply substitute this omega as omega c, and this LC goes here, and you take under root of that, and omega is 2 pi fc. Omega c is 2 pi fc. So substituting omega c here, you get fc to be equivalent to 1 upon pi under root LC, which is the cutoff frequency of a low pass filter that we have already used in solving a few numericals in another video. So this is how we get this. The rationale behind setting this frequency as the cutoff frequency is now clear, because this is the point where the impedance shifts from being real to imaginary. And on the contrary, if you substitute or simplify this thing, ZOT, so you get L upon C under root to be equivalent to R naught. You can substitute this quantity, which is going to be real anyways, or this is our good old K, so very famously known as the constant K of a filter. And this is from where we've gotten this formula.
Do you know that there's a part of your brain that sets the goals, and then there is another part of your brain that helps you achieve?
From where we've gotten this formula. A constant K type prototype filter has a constant K which is equivalent to under root L by C, and it's also denoted as R naught at times. And simplifying this thing, if we substitute omega C square is equal to 4 upon LC, we get 1 minus omega square upon omega C square. So in other words, this formula again becomes very, very important if you've been given the frequency of operation for certain frequency. Let us say you have a frequency 2 hertz and your cutoff frequency is let us say 1 hertz. Then you can find impedance of the low pass filter at 2 hertz frequency by substituting 2 hertz here, 1 hertz here, and of course 1 kilohertz is more rational, and by substituting the values of L and C you can find how much impedance is being offered by the low pass filter at certain frequency, or you can check if this frequency lies above the range of pass band, then is it really offering you an impedance which does the job for you or not. So that is how you calculate ZOT, R naught, omega C, and all those stuff. So I hope this tutorial was of help, and you've gotten to understand how to calculate the characteristic impedance of a 2-port network. In the next tutorial we'll talk about the 2-port networks with pi sections, and of course the key point remains the same, that for filters the output impedance, it needs to be kept equivalent to the so-called input impedance, which is also our characteristic impedance. And once we get the characteristic impedance, we simply have the job of putting the values of L and C's in that equation to get the final formulas that we use in our numericals to design filters. It could be low pass filters of T section, low pass filters of pi section, and high pass filters of T section, and high pass filters of pi section. But the theory remains the same. You simply need to find out Z or T and then proceed on from there. Not exactly Z or T, but Z naught, which is the characteristic impedance. And I hope this tutorial was of help. If you liked the video, give it a thumbs up, consider subscribing to the channel, share this video as much